All right, welcome to calculus. So we're going to look at integration by parts. I have another video where I explain the basics of this, and here I'm going to work through two examples. One of them is pretty straightforward. The other one, it can be aggressive, and I will warn you on that on the front end. So take some time with the second example, especially that I run through here. The first one is pretty straightforward, with one little exception. Okay, I always pick the u and then I pick the dz, right? My u here, as a general rule, I almost always pick which part of the expression is going to degrade faster, meaning which one is going to reduce in degree or reduce in the number of terms we get the fastest. Now in this instance, I'm actually going to go against that general rule simply because I have a logarithm. So this logarithm kind of trumps that idea. And this is why. So when I do ln of x, the du, the derivative of that is 1 over x dx. Now, the reason why I picked ln is because now I'm switching this logarithmic function into a rational function. Rational functions and polynomials can be multiplied and normally reduce on some level, especially when the denominator is a single term. That's going to make my next step a lot simpler. The second reason for this is it's much easier to do this integration of ln of x than it is to do, it's much easier to do the derivative of ln of x than it is to do the integration of ln of x, which is another factor in how I choose my u. I always choose the u first because I'm thinking, what can I do the derivative of rather easily, and what part of the function is going to degrade the fastest and the easiest for me. And on the surface, you think the polynomial is going to degrade faster, but in actuality, ln is actually the piece that degrades faster here. So ultimately, my rule still holds true. And then you get the other part, which is x squared plus 3 dx. So that integrates into x to the third over 3 plus 3x. All right, now notice I'm not putting the plus c here, okay? Because we're going to do an integration later on, and we're just going to have another constant we're adding on there. So we don't want to introduce new pieces just yet. So I do my uz, so that gives me ln of x times x cubed over 3 plus 3x, and then minus the integration of 1 over x cubed over 3 plus 3x. All right, now this is where this is nice, okay? We have this 1 over x, which will cancel with x cubed, leaving me with a 2 there, and it's going to cancel outright with that one, just leaving me with 3. So this piece is now gone, right? So now what I'm doing there is I'm doing the integration of x squared over 3 plus 3 dx. That integration is really straightforward. That's just going to be x cubed over 9 plus 3x. And then there's my plus c on that. Okay, make sure I put my parentheses in there. So now I have ln of x, and then x cubed over 3 plus 3x. And there we go. Now notice I didn't put the plus c inside that minus sign. Ultimately, this is a constant. We don't know what the constant is, whether it's positive or negative or anything else. So it doesn't really matter where we put it in relation to any other pieces, as long as we are adding it on or subtracting it into that expression at some point. So I always just put plus c on the end of it without any regard to whether it's actually supposed to be minus or plus, because if we were to solve for that particular value of c, it would work its way out regardless. Okay, so now what can we do? Well, here's another example, and this one is a little bit more aggressive. Okay, on the surface it seems really straightforward. E to the x and sine of x. Now this is definitely an integration by parts because these two are completely unrelated. So we can let u equal something and we can let dz equal the other piece. I'm going to go ahead and tell you it doesn't matter which one you choose. It's not going to make any difference here. So you choose whichever one of these things makes more sense to you. So let's let u equal sine of x and let dz equal e to the x. I do that because doing the derivative of trig functions I find to be a little bit more straightforward than doing the integrations, because I always think in terms of integration or derivatives with trig functions. Even when I'm integrating, I always think about the other direction for them. So the derivative of sine is cosine of x dx there, And the integration of e to the x is e to the x. I forgot my dx on the end of that little piece there. Right, so now I have, and I'm gonna write this one a little different the way I wrote the others, and you'll see why after a bit. So this is integration of sine of x dx, and this is always true, I just didn't write it on the others. And that's equal to sine x times e to the x minus the integration of e to the x cosine x. The order doesn't matter, okay? So we still have an exponential times a trig function. All right, so if you've seen my other video, you see now what we do is we pick another u and dv, and if you want to relabel them with different variables, you can. So you can call them v and say dw, and then you need to find dv, and you need to find w. Now, the only cautionary tale I tell you about this is whenever you're doing integrations and you have to, integration by parts, and you have to do multiple stages like this, I would encourage you to keep the same tone that you started with. So if you let u be sine, I'd let v be the trig functions. If you start off with u being the trig functions, I'd let v continue to be the trig function. So in this case, it's cosine of x. And then that derivative would be negative sine x dx. And you have e to the x dx as your dw, which means that w is e to the x. Now, the reason I do that is it just seems to make things work out a little bit more straightforwardly for me. Is it the best way? Well, it's the way that works for me. I'm going to leave it at that. You can try it if you to switch them up if you want. I find it to cause more confusion. Okay, so we've just got to rewrite the first part of all this that we've already done, minus, and here is where it starts to get a little messy with the signs and all that. So it's minus this integration, so that is e to the x cosine of x minus the integration, but it was already minus, so it's now plus the integration of dv and w, and that is e to the x negative sine x dx. You might need to pause and just kind of prove to yourself that these signs do in fact match up. So we had a minus sign right there that we had to distribute through, because remember, now what we're doing is we do v w minus the integration of w dv, right? dv was negative, right? You're doing that minus, so you're subtracting off that integration, and it was already subtraction. So that's three minus signs in a row there that make you two of them cancel, give you a positive, and then you have the third one left there. Now notice, and this is the really fun part, notice that this piece right here and this piece right here are the same. Okay, and to be a little bit more descriptive about that, the integration we just ended up with, the last integration piece that we ended up with, matches the original function, the original expression that we had, that we started with, except for a sign difference. So if I were to just simply add e to the x sine x dx to both sides, I essentially am combining like terms here. All right. So I'm just going to add that to both sides. It's an equation, so I can do anything I want, remember? So now I have 2 integration of e to the x sine x dx equals sine x e to the x minus e to the x cosine x. So that means you divide by 2. Those 2's cancel, and over here do the same thing, divide by 2. Now notice on this particular piece here, we don't have the plus c. Where did the plus c go? Well, we never did this other integration piece to add it in, right? So is it wrong to do this? No, actually it's not, because you're still, even if it's 0, and this is the thing to remember, is that this c value might be 0. You're not going to be affecting anything. When in doubt, put the plus c on the end of there, right? Because worst case scenario is c is 0. But if c is some other value, you want to make sure that it's there. Okay, so you're never going to damage the equation, if you will, by putting plus c on there. But you will if you leave it off inappropriately, because if it's not there, you're implying that that is the particular solution. If you put the plus c on here, you're saying this is the general solution, and we just don't know what that value is there. If you leave it off, you're implying that that value of c is 0. In this particular instance, we're kind of having to superficially put it in there because we never officially did that integration right there at the end anyway. All right. So I hope these equations are useful to you. I hope the processes help you understand calculus better. Integration by parts is probably one of my most favorite aspects of calculus, oddly enough. And I have a couple of others I really enjoy as well. If you need additional videos or examples about any of this, please reach out and ask. And I hope that you find calculus to be enjoyable in your life. All right, take care.